Swayam Prabha. Digital India. Educated India.
So, last class I was solving one particular problem on two-way eccentricity, and I determined the effective length and width of the foundation. Now, today I will solve the remaining part of that problem. So, this was the problem that a foundation of width 3 meter and length 6 meter was placed at a depth of 1 meter. From the ground, and the EL value is 1.2 meter and EB value is 0.3 meter, and I have determined the effective length, which is 5.28 meter, and effective width, which is 1.875 meter. Original length was 6 meter and original width was 3 meter. And now we have to use the Meyer-Hoff equation, and then we assume the general shear failure and the factor of safety is 3. So, now if I use the Meyer-Hoff bearing capacity equation, so that equation for Q net ultimate, which is the CNC SC DC IC plus Q NQ SQ DQ IQ plus half B or B dash here, gamma S gamma D gamma I gamma minus gamma df. Okay, so, as there is no it is a perfectly vertical load. So, IC IQ I gamma will be equal to 1. So, now let me determine that those bearing capacity factors or correction factors. So, SC equation is equal to I know that this is 0.2 and tan square, then similar to 45 degree plus 5 by 2 means 20 degree by 2, and that is B dash by L dash, and B dash is 1.875 and L dash is 5.28. Okay. So, this is 5.28, yes 5.28. So, now this value will be 1.145. Similarly, that SQ will be equal to S gamma is 1 plus 0.1 tan square 45 degree plus 20 degree by 2, and this is B by L B dash by L 1.875 divided by 5.28, which is equal to 1.072. Similarly, I can calculate the DC also. This is 1 plus 0.2, that is df, which is 1 by B dash 1.875, then tan 45 degree plus 5 by 2. So, this value is 1.152. Okay. So, now the dq equal to d gamma is equal to 1 plus 0.1, 1 by 1.875 tan 45 degree plus 5 by 2, which is equal to 1.076. Okay, so, net ultimate bearing capacity, which is equal to 100 into 14.8 into 1.145 into 1.152 into 1 plus 18 into 1 into 1.072 into 1.0676 into 1 plus half into 18 into b dash is 1.875 into 2.9 into 1.072 into 1.076 into 1 minus 18 into 1. So, this is the gamma b dash 2.9, then these two factors. Yeah. So, now this value is coming out to be 2123.5 kilonewton meter square, and Q net safe is equal to 2123.5 divided by 3, which is 708 kilonewton meter square. Now, the Q safe will be equal to Q net safe into A dash. So, that is equal to 708 into 1.875 into 5.28. So, that is around 7000 kilonewton. So, which is roughly 7 meganewton. So, you can see that in previous problem I consider the one way eccentricity and the safe load was around 10,000 kilonewton, but now here I have taken the two way eccentricity. So, the effective area has been further reduced, and then the total load, safe load, now the footing can carry is 7 meganewton, okay, or the 7000 kilonewton. So, which is reduced compared to the first case. So, now the next problem that I will discuss, or that I will explain, that how I can use the case 4 to determine the effective area of the foundation. Okay. So, now this is the similar type of problem, only difference is that here the EL is taken 0.6 meter and EB is taken 0.3 meter. So, now my L is equal to 6 meter and B is equal to 3 meter. Now, L is equal to 0.6 meter and EB is equal to 0.3 meter. Okay. So, now EL by L is equal to 0.6 divided by 6 is 0.1 and EB by E is also 0.1. Okay. So, now the case is this is both are EL by L also less than 0.167 and EB by B is also less than 0.167. Okay. So, that means it is case 4. Now, here we have to determine only the effective area, because I have already discussed that once you get the effective area or effective width and the length, how we can determine the ultimate bearing capacity or the safe load that can be act on the foundation. But remember that I have discussed only the Mehrab method, but you can use the other methods also, like the Hansen method, then the VII method, or even IS code method also. But in case of Tazakis, this option is not there to incorporate this loading eccentricity. But remember that when you use the other methods, then you calculate the correction factor according to their suggestions. Okay? That means, some cases you have to use B and L, and some cases you have to use B dash and L dash. Remember that when you, because in Mehrab all the factors are calculated by using B dash and L dash. But in case of, say, for example, Hansen shape factor and the inclination factor, you have to use effective area or B dash and L dash. but for the depth factor you have to use B and L. Similarly, for basic all the factors you have to determine by using B and L, not B dash and L dash, except that inclination factor effective area, that area that you have to use as a dash, okay, effective area. So, and the for IS code method also all the factors are to be determined by using B dash and L dash. So, you just keep in mind that all based on their suggestions, and I am given as a note for all cases, that when you have to consider the actual width or length, when you have to consider the effective width or the effective length. Okay. So, determine those factors according to that. So, and it is case 4. Now, case 4, the effective area is given L2 by L2B plus half B plus B2 into L minus L2. Okay. Now, the B2 by B. So, now here this is 0.1, this is also 0.1. So, this is 0.1 EB by B and EL by L also 0.1. So, that means this is 0.1. And if I use that upward curves, so that means this is the value, and which will give me the B2 by B. So, upward curve B2 by B. So, that is this value is roughly this is 2, this is 0.24, 0.24. So, this is the curve. Okay. So, this is the curve that we have to use. So, this curve we have to use for the to calculate the B2 by B. Now, for the downward curve, so these are the values. So, this is 0.02, 0.04, 0.06, 0.08. So, this is 0.02, this line. This is 0.04, 0.06, 0.08. So, this is the line. Okay. So, this is the line which is coming from here and passing from here. So, this is the line and which is roughly passing from here. So, more or less the same value. So, here this the downward curves will give me the L2 by L. So, L2 by L is equal to 0.22. Clear? So, one is 0.24 and is 0.22. So, now my B2 is equal to 0.24 into 3, which is 0.72 meter, and the L2 is equal to 0.22 into 6, which is equal to 1.32 meter, and now I can calculate the A dash, which is this is L2 is 1.32 into B is 3 plus half 3 plus B2 is 0.72, then 6 minus 1.32. So, that effective area is 12.7 meter square. Okay. So, now the B dash is given, L dash is L, which is 6 meter in case of case 4. So, B dash will be L A dash by L dash. So, A dash is 12.7 and L dash is 6. So, B dash will be 2.1 meter. So, this way you will get the L dash and the B dash. So, and now you can use these effective width and length to calculate the bearing capacity of the foundation. So, now I have discussed the one way eccentricity and which equation you should use for one way eccentricity, and then I have discussed the two ways eccentricity also, and then I have discussed 4 cases, and then I have discussed how to calculate the effective length and width and the area for 4 cases, and then how you can use those effective width and length to determine the bearing capacity. So, in the next effect, so is the if the load is not vertical, it is inclined, or it is not vertical, it is inclined, then how I can determine the bearing capacity. So, that means the foundation under inclined load. Okay? So, foundation under inclined load, then how I can take care of that effect. So, first a simple problem I am discussing, then I will go to some complicated problems, and then how to use different approaches in case of inclined load. Because for eccentric loading, all the approaches are same. That means, you have to only know that how you can determine B dash and L dash. Then based on the given suggestion, by different methods or different theory, you put the B dash, L dash or B or L, and you will get the bearing capacity. But for incline loading, it's not it's slightly complicated, specifically for the Henson theory, because if the Henson theory you want to use, then under inclined load you have to take care so many things. So, that I will discuss in this part. So, that foundation under inclined load, the same problem, more or less I am taking the same problem, and only certain conditions are changed. So, that means the rectangular footing of size 3 meter by 6 meter is placed at a depth of 1 meter in a C5 soil. Okay. The water table is at a great depth, unit weight is again 80 kilonewton per meter cube, and at 800 kilonewton load acts at an angle 15 degree to the vertical at the center of the foundation. That means, there is no eccentricity, load is acting at the center, but with angle 15 degree with vertical. Okay. Now, there can be case that it is acting at an angle, but with an eccentricity also. So, that means, in that case both the conditions you have to consider, but here I have not considered the eccentricity, I have considered only the inclination effect. So, the footing is such that the load is acting. So, that means, this is vertical. So, load is acting at an angle of this is vertical, load is acting at a angle of 15 degree, and that load value is 8000 kilonewton. Okay. And then we have to determine the factor of safety against bearing and sliding. Assume the general shear failure, take delta is equal to 0.85 and C is equal to 0.7 of C, and remember that why I have to, because for previous cases I have to check only the bearing capacity, but here you have to check the sliding also, because when the load is acting, there is a vertical component, there is a horizontal component also. So, vertical component against the vertical component you have to check the bearing capacity, but against the horizontal component you have to check the sliding also, because not only it will push the foundation in downward direction, but the horizontal component also try to slide the foundation. So, we have to take the sliding also. That is why this delta, because this delta is the friction angle between the foundation and the base soil, and this addition is the addition between the foundation and the base soil. Remember that this is base soil, and why you have to consider the neglect the passive resistance. For example, suppose we have a foundation and this is my depth of foundation. Okay. Now, there is a inclination of the load. So, load is acting with an angle, it is inclined. So, it has two components, one is the vertical component and another is the horizontal one is the vertical component and is the horizontal component. So, now that means this horizontal component will try to push the foundation or slide the foundation from right to left. So, that means the soil in this zone basically will give you a passive resistance. So, soil, so from where I will get the resistance? So, I will get this passive resistance as well as I will get this resistance from the base soil, because your foundation is sliding. So, in our retaining wall design also and this type of foundation design, we neglect generally passive resistance, because if we do not consider the passive resistance, then and if my foundation is safe, then if I consider the passive resistance, obviously it will be over safe. So, that is why you can neglect the passive resistance, but if you want to accurately determine the factor of safety, or then you have to consider the passive resistance, but here the passive resistance is not considered. So, passive resistance means if you consider the the ranking passive force, how to calculate, that means you have to calculate that this P p, which will be half gamma d f square into K p, where K p will be equal to 1 plus sin phi and 1 minus sin phi. Okay. So, this is gamma d f into K p, and d f is the depth of foundation. So, that amount of passive resistance. So, this soil is given. So, this is P p, this is H, okay. And then you will get another shear resistance along this line. So, that is the shear resistance you will get, say T. So, finally, the net force or the shear resistance is that. So, that means your factor of safety or the factor of safety will be equal to this T plus P p divided by H. H is the horizontal component of the load and V is the vertical component of the load. R is the resultant here, which is 8000 kilonewton. Clear? So, but in this case we have not considered the P p. So, our case the factor of safety for sliding, this is for sliding, will be this T and this divided by H. Okay. So, because we are neglecting this P p part. So, now let us solve this question. So, that means we are calculating Q net ultimate, which is a Q ultimate minus gamma d f. So, then this is the expression which I am using, or in number of cases I have used in number of times. So, for as it is a general shear failure. So, for N c value corresponding to phi equal to 20 degrees be 14.8, N q and N gamma also we will get from the Mayer of bearing capacity factor table. Then I will calculate the safe factor S c, S q, S gamma by using these expression, because here no eccentricity. So, you have to consider, you have to take B and L, and then I will calculate the depth factor also, depth factor, and now the inclination factor, they are not 1. Now, this inclination factor I c, I q, this alpha is 15 degree, and then this alpha value is 15 degree, and this is phi, because alpha is with vertical, because alpha is given this with vertical, and so that means this is 15. If you put the 15, I will get these correction factors. Now, if I put these values in the equation, finally, I will get one value which is 1421.4 kilonewton per meter square. So, net ultimate bearing capacity is 1421.4 kilonewton per meter. So, now we have to calculate the factor of safety. So, as I mentioned, the vertical component will against the vertical component we have to check the factor of safety against bearing, and against the horizontal component we have to check the factor of safety against the sliding. And so that means this is, as I mentioned, this is the T, and which is basically that T value is equal to the vertical component which is acting T is the shear resistance that the foundation and the base soil is given, which is so vertical component V into the tan delta plus the effective area into the cohesion addition. Okay. So, total vertical 4 into tan delta into the effective area and the addition, and that is T. So, factor of safety is basically T by H, because we have neglected the passive resistance. So, this is the vertical component tan delta and then the area into C A. And remember that if in your case it is eccentric loading, then you have to use A dash, not A. In case of eccentric loading, you have to use the A dash, but now for particular case that A dash is equal to A, because there is no eccentric loading. So, effective area is equal to the actual area of the footing. So, now what is the bearing capacity? So, net ultimate bearing capacity is this one. Now, if I multiply with the area in case of eccentric footing effective area, then I will get the total load carrying capacity of the soil. So, that is total vertical load carrying capacity of the soil. Okay. Now, if I divide it with the vertical component of the load. So, vertical component how I can get? So, suppose this is my R and it has a horizontal component and the vertical component V, and this is H. Now, the horizontal component. So, this angle is 15 degree. So, this angle 15 means this angle also 15 degree. So, the V will be P into cos 15 degree, or if it is say P or R. So, now here it is P is written. So, you can write P also. If this is P, so P cos 15 degree and horizontal component will be P sin 15 degree. So, this is the value, and P is equal to here 8000 kilonewton. So, now if I take the area into the net ultimate bearing capacity, I will get the total vertical load the foundation can take divided by the total load which is acting. So, I will get a factor of safety 3.31, which is greater than 2.5, fine. Okay. Now, let us check the sliding. So, now this is the, as I mentioned, T by H, T is equal to this equation. So, this is vertical component into tan delta, and delta is here taken 0.8 times of the friction angle, and the addition also taken 0.7 times of the cohesion value. And because in Hansen and the basic, it is recommended that you can take 0.6 to 1 times of the cohesion. So, I have taken 0.7 times of the cohesion value. So, this is the area 3 into 6, the 0.6 times of the cohesion is 100 and divided by the horizontal force. So, horizontal component 2070.6. So, 2070.6. So, it will give 1.68, which is greater than 1.5, fine. So, this way I can check the bearing capacity and the sliding in case of inclined load. But here one thing I want to mention, that here directly your inclination is given. Okay. And so, that means suppose if you have a footing like this, now inclination can be in any direction, na? I mean any two directions. That means, the load can be inclined in this direction, that means it is inclined along this length direction, it can be inclined along the width direction. So, inclination can be in any direction, it can be in the width direction, it can be in the length direction. But here if you use the Mayer bearing capacity equation, because we have used the Mayer bearing capacity equation, because it is not required to know that your inclination in which direction. Okay. So, that means the inclination, if we know that what is the amount of inclination with respect to vertical axis, that is good enough to calculate the bearing capacity as per Mayer. bearing capacity theory. Okay. So, that means here we know that it is acting with an angle of 15 degree with vertical axis, then that is good enough. So, now these inclination load can be parallel, the horizontal load can be parallel to width or can be parallel to length, but it is not required to know to solve as per the bearing capacity equation proposed by Meyer. But if we use the Henson or the basic bearing capacity equation, then we should know that which direction this horizontal component is acting, whether it is parallel to B or parallel to H. Okay? Or in other way you can say that that it is required to know, another way you can say that we can incorporate the direction of the horizontal loading also in Vesic and Henson, that we cannot do in the Meyer. Okay. But that is the requirement, so you can do. So, but Meyer equation, it is good enough to know the inclination angle with respect to vertical, but Henson and Vesic we have to know that in which direction this horizontal load is acting, whether it is vertical width direction or the length direction. So, in the next class I will discuss that if you want to use the Henson and the Vesic, then how you can incorporate this the direction of the horizontal load in the bearing capacity equation. Thank you.